Yeah, go ahead.
All right, thanks for inviting me. Thank you for coming, everyone. I got some good news and some bad news. Good news is this talk will have many videos and few differential equations, so it'll be perfect talk for the fourth day at the end, just before dinner. The bad news is this was the fourth day, so I had a lot of time to listen to other talks, and every time I heard something, I added a slide. So this may be long. I'll do my best not to make it long. My name is Mario Jurić. I'm from the University of Washington. I'm an astronomer, supposed to be an astronomer. I work with computers mostly. But I'll start with a simple question, which is, what is an astronomer? For those of you who are not astronomers, if you go to Google, and the way how I learn things is I just go to Google and type in keywords in Google image search. An astronomer is typically a person who has a telescope and looks through the telescopes, and through the telescopes looks at the sky. So this is sort of the classical view of what astronomers do, what people think astronomers do. We think we get to go to mountains, we observe with great telescopes, we take images, we bring those images home, we study those individual images, find the objects that we want to study, and come up with some new interesting discovery. But what we increasingly do is slightly different. What we increasingly do is we build these large special purpose survey telescopes. We put these large special purpose wide field cameras onto those survey telescopes that can capture very large images of the universe all at once. We then build large software systems that take those data, process them automatically, identify objects for us, figure out their properties, and then store them into large databases. And then we serve those most likely online. And then that's where the science begins. So today, astronomy has really changed from one person with a telescope looking at one object to something survey like this. So let me give you a bit of a sense of that. How many of you have seen this image before, just somewhere on TV or someplace? Right, this is one of the most iconic images from the Hubble Space Telescope called Pillars of Creation. It was in Star Trek: The Next Generation, I think, first episode. This is an active star-forming nebula. Here's where stars are born and so on, and here's our lovely Hubble Space Telescope there. How big do you think this thing is on the sky? This is how big it is. So this is a telescope that really zooms in and takes beautiful images, but of very small areas in the sky. So this Sloan Digital Sky Survey telescope is what I have here. This is one of the first groundbreaking survey telescopes. How big is a single image that it takes? This is how big it is. So we're going from something that Hubble could take, which is just this little piece, to one image that's of this size. And you know what we do with these telescopes? We don't just take one image. We take one image every few minutes until we get things like this. So this here is the Sloan Digital Sky Survey data set. It took 10 years to collect all these data. It's over 1.2 billion observations of stars and galaxies. This here is half of the sky. This is visualizing one hemisphere. It's approximately 20 terabytes of raw imaging data. This is one of the first surveys. This started in 1998. And these first few phases went through 2009. And all these data are now in large databases for astronomers to use. So that's interesting, but how big of a deal, does that actually produce science to build these kind of automated survey telescopes? And what I did was, one of the nice things we have in astronomy is we have the service called ADS, where we can go and look for how well sighted certain telescopes or certain surveys are. And if you type in Sloan Digital Sky Survey or SDSS, you find that it's got 3,000 citations, 3,000 papers written from the data of SDSS with 240,000 citations to those papers. And the age index is 210. Now, that is more or less meaningless unless I give you something to scale it with. And let's take Hubble Space Telescope. Right, that is a very well-known machine up there that has changed science in many different ways. The numbers are almost the same. So they're at the same scale. So this is what I'm trying to show you here is not that SDSS is better than Sloan, right? The very first, SDSS is better than Hubble. The very first paper here is the Nobel Prize winning one for the expansion of the universe. So there are some qualitative differences. But what I'm showing you is that this type of survey science, where you don't go and zoom into one single object, but you go and decide to collect the data from the entire sky, put it in a database, and then open it up to thousands of people to work off of it, makes a lot of sense and is really, really, really effective. So with that switch to survey science, what do we as astronomers increasingly do? Most of us don't even go to telescope. Last time I was at a proper telescope was, I think, 20 years ago. I'm sad to say, actually observing, just an asterisk. What we do is we devise algorithms to analyze huge databases and draw inferences around about the universe. And we employ machine learning, we employ data science. And in many ways, it's not an accident I'm in Seattle. Our work day to day has more in common with someone in Microsoft or Google than with our predecessors 20 years ago. And I think this is a large part of why we are here, part of this collaboration as astronomers. And this is a dramatic shift in what an astronomer is and what skills we need to be successful. So this is why the institute that I'm at exists. So I come from the University of Washington. We have their institute called the Data Intensive Research in Astrophysics and Cosmology, and or short for DIRAC. This is an internal joke because Dirac was famously a theorist and wouldn't touch data, and we named the Data Science Institute after Dirac. Our first director was British. He has a strange sense of humor. So our mission is to develop these kinds of astronomical data sets, algorithms, and software, and then use them to explore the universe. And we try to bring together the diversity of expertise that we need to do that and put that together. And this is what we're hoping to contribute to the SMASH collaboration as well, especially the students who want to learn these types of things. All right. This was an introduction. So the next big trick that we hope to do in survey science is this observatory. This here is the building of the Rubin Observatory. This is in Chile. It's a new special purpose observatory being built to do a most comprehensive, deepest sky survey ever in human history. We're going to have repeated imaging of visible sky to 24th magnitude. We'll operate for 10 years. We'll collect about 60 petabytes of raw data. This will give us about 30 trillion observations of roughly 40 billion stars, galaxies, and asteroids. Here is the observatory. The outer building was essentially complete almost 2 years ago. This is when I was there in 2023. This is what you see when you step inside. There's this beautiful telescope mountain assembly that will hold an 8-meter mirror. When we were there, the mirror was not installed yet. I'll show you that at the end. This is the more impressive version of that picture. This one moves. This is not a time lapse. So there are some stairs down here that give you a sense for how tall a human should be. So this is about 250 tons of glass and steel that can make a 180-degree accelerate, make a 180-degree turn, and stop and be ready to observe in 18 seconds. So it's really an engineering marvel. And the reason why you don't see any people here is this is so tightly packed that it's too dangerous for a person to be in there when the telescope is moving. If you were Usain Bolt, the current world record holder for a 100-meter dash, you wouldn't be able to outrun the top of this telescope if it started rotating at its maximum speed. That's how fast it's moving inside. This here is the mirror for the telescope back in 2008 when it first came out of the oven. This here is that mirror in 2015 when it was polished. Here are some of the same people with a lot more gray hair. And this is the mirror in 2024, now on the summit, when it was aluminized, when it was coated so that it's actually reflective and shiny. I love seeing this picture because take a look at this. So this is the mirror in the coating chamber, and now don't blink here. And boom, now it's reflective. It's yeah, I asked if this was like a cut or they messed with the video, but no, this is how it happens. So we have the mirror now. It's up there as of April. Here's the camera. Camera is the size of a small jet engine. About 200 ccds here up front. This was it in 2022 at SLAC. Here it is complete. You can see the chips up here. The size is roughly this big. So that's how many ccds you have in the same technology, well, similar technology to what you have in your phones. And this is the camera getting ready for the move. These are These are all the luggage that the camera needed for the move to Chile. This was at Slack when it was all packed up and parked. And the camera itself is in this final container. We loaded it all up onto a Boeing 747 that was leased to fly the camera from San Francisco to Chile. It's a very funny story that I can tell on camera. So ask me during the coffee break, why did we have to lease a 747 to fly down there? Here's camera going up to the summit on May 15. Note that this is all happening recently. And then here it is unpacked on the summit. Now, there are some other pieces of the telescope. Here is the secondary mirror. Secondary mirror itself is like almost 3 meters in size. So that would be a decent sized telescope all on its own. That's been installed in August. Then a commissioning camera. This is the camera for testing. It got installed on August 23rd. And the final piece was installed just 1 week ago. So this mirror that I was showing you was taken out of the coating chamber, put on a lift. This is really cool. You'll get a feel for what the observatory looks like on the inside within the next shot. So this is the elevator, goes up. And now we have to lift the roof. See what happens there? And now that it goes in. This mirror took 10 years to build. If we smash it, this project doesn't happen. So everyone is incredibly careful about everything that has to do with this mirror. This is the one thing that must not have any kind of an accident. And now it's under the telescope, and we bring it up, and it's bolted. Yay. This is it. We have a telescope. After 20 years of R&D and construction, the telescope is now complete as of October 3rd. So what's next? Next, we're going to commission it. We're going to test it. In about 3 weeks, we expect first data. I said that mirror is the most precious thing in my own personal universe. We're going to very carefully start moving the telescope just to make sure that nothing breaks the mirror. That's why it takes 3 weeks from constructing it to first data. And then after about a year of testing, we'll start the legacy survey of space and time, which is that telescope covering the sky like this animation shows here. So it'll go to 500 different places each night. It will repeat. It'll take 2 visits, 2 images of each pointing every night. Each of those images is 10 square degrees. That's about 40 times the size of the moon on the sky, or the area of the moon, just to be precise. That gives you about 4,000 unique square degrees every night. The whole sky has 40,000. And we repeat that for 10 years. And that gives you the most comprehensive survey of the sky ever. To compare it to that image of SDSS that I showed you, remember, SDSS has, 3,000 papers written with this data set and 200 and something thousand citations. In terms of the data volume, this is one night of Rubin. So we're going to really amp up this field significantly when data start flowing in less than a year. Okay, so now we're getting closer to science. If we just took 6 petabytes of data and dumped it onto all of you, onto all of us astronomers, that wouldn't be very useful. So one of the things that we're going to do, and we spend almost 1/3 of the budget of the project, is to write software to process those images, to take out instrumental signatures. This is what we talked about yesterday, this morning, before lunch, felt like yesterday. And produce instrument signature corrected images for everyone to use and everyone to be able to download. But we have to go a step beyond that, because even those images are quite difficult to work with. We're talking petabytes, tens of petabytes of images. What we're going to do is we're going to produce catalogs. We've developed software that identifies every single speck of light here, tries to figure out what it is, measures its properties, and then stores it as a list of catalogs that correspond to physical objects in the sky. So to give you a sense of what the relationship of the images and catalogs is, especially if you're a computer scientist, you're going to like this. These are images. This is from the Deckel survey. It's an online viewer. Oh, I forgot to add the URL. I'll add it later. So here are the images of the sky. And then in my next slide, you basically didn't notice any difference between the first and the second slide. What's in the second slide is an image reconstructed from the catalog. We took that catalog. The catalog tells you where the objects are, what their shapes are, what their colors are. So we can reconstruct that input image from the catalog. It practically looks the same. If you difference the two and amp up the contrast, then you start seeing some differences. But the way to think about a catalog is it's a compressed representation of the image that goes in. For the scientist, the catalog is something that's physically meaningful, but also for computer scientists, the one way to think about it is it's a compression technique. It's a lossy compression of the image that goes in. By the way, this is now, since AI has claimed physics or vice versa, this is now my claim to computer science. So I expect a Turing Award for some of these discoveries at some point. So we've got images and catalogs, and those are the things that we're going to offer to the public, to the academic public, and hopefully they will produce some science. So let's talk about that science. We have four main areas, four main science themes that we're hoping to cover. Dark matter and dark energy. We're trying to map the Milky Way. We're trying to map the solar system, find out what we have in the solar system, how the solar system began, and we're trying to explore the transient and optical sky, understand things that change in the universe. If you squint a little bit, you'll notice that this essentially covers all of astrophysics, and that is not an accident. Once you reach a certain scale in the size of the telescope and the speed with which you can image the sky, you essentially can serve many very different areas with the same machine. And that's why this machine got built, because with the same machine, you can measure the solar system and tell the world what dark energy is, which is quite amazing. So let's talk a little bit about some of these fields. Probing dark matter and dark energy. Jurić gave an excellent talk about the details of the state of the art here and how we're going to do this analysis. So I'll just stay at a very high level and give you a sense of some more specific, a few more specific details. So we know that only 4%, we understand only 4%, we somewhat understand only 4% of the universe, and then we don't understand the other 96. And a big part of what we're doing, what our colleagues in particle physics are doing and elsewhere is understanding this part and that part. The way we do it in astronomy to understand dark matter and dark energy is we try to map out where dark matter is. We've heard excellent talks earlier this morning, from dark matter at small scales to Jurić's talk about dark matter and dark energy at larger scales. And for dark energy, what we're trying to figure out is essentially how the universe expanded over time. And the way you do that is you try to observe literally billions of galaxies, on order of 4 to 10 billion of galaxies. And then for each galaxy, you try to estimate how far it is. Far means also looking back in time. Based on how far it is, based on some other properties, you can try to understand where we are in these curves, whether the universe has been expanding faster or slower in the past, and what might be the nature of dark energy. Determining that distance to galaxies is the core problem here. The way you would usually do that is you take a spectrum of a galaxy. You take a spectrum, you see these spectral lines. If the galaxy is farther out, it is what we call redshifted. So it's moved on the absolute x-axis and this way. You would look at where these lines are, and that's how you would know where the galaxy is. Now, taking a spectrum of each galaxy is impossibly expensive. Best we can do is we can take an integral of the spectrum in these 6 bands, U, G, R, I, Z, and there's Y here for Rubin. This is from a previous telescope. So the question is, can you infer what's going on with these spectral lines by just getting an integral of the spectrum across in these 5 or 6 different areas? And the answer is you can. This is what's called the photometric redshift. Here's an example. There's a photometric redshift on the x-axis, and there's the true redshift on the y-axis. If everything was perfect, we had a straight line here. You notice that things are not perfect. There are outliers and so forth. This has fueled dozens and dozens of PhD theses, how to optimize this, how to make this go more towards a line and make the outliers as uncatastrophic as possible. But one way people have started looking at this is what I just showed you as a traditional way of doing it, but like, can we use machine learning to do it? So this was a very interesting paper that came out in 2018, where what they've done was they ignored this entire business with colors and so forth, and they took images, because images do encode color of the galaxy, not just color, but shape. So they fed a neural network with about 400,000 images of galaxies from SDSS that had spectroscopic redshifts available, and trained it to predict from the image what the spectroscopic redshift is. And look at the agreement. It actually outperformed the best known photo Z estimators, traditional photo Z estimators, by a factor of few, because not just the neural network figured out that it's not just the color that is different, but that galaxies have different shapes at different points in time in the universe, and it can use that information. So that's how it can reduce the catastrophic outliers dramatically. So this was, I think, one of the first eye-opening experiments where it was like, oh, okay, this is interesting. Then the question, once you realize that, you can go beyond that for, let's say, galaxy classification. So this here is a famous Messier 51 object. These are two galaxies, the Whirlpool galaxy, two galaxies actually that are interacting. You can ask questions such as, can AI find galaxies like that are merging or that have what we call bars? So here's a fairly simple CNN trained on 15,000 galaxies by Dominguez Sanchez, also in 2018. You can tell the architecture is not that complex. The convolutional layers, a couple of fully connected layers, and out you get the classification in the end. And how well does it do for classification of mergers and bars? Well, first of all, it outperformed everything else that was out there before computationally. And then it also outperformed humans. It got to a point where it was indistinguishable from humans, right? Because humans fed the labels in, so you cannot like really outperform humans in that sense, or the biggest expert, because that's your training data. And the remarkable thing to me is that this was done using a fairly simple CNN. I use this as an example in some of my classes when I teach undergraduates. Like this is what it takes. So the reason why I like to show this is, especially to non-specialists, we've sort of scared people into thinking that AI is something sometimes always incredibly sophisticated that we cannot grasp and we can maybe use. But no, we can actually understand how to build some of this. Or we can understand how to teach people to build it on themselves. So let's go on through this tour. Exploring transient and optical sky. We've heard about the tidal disruption events when a star comes close to a black hole and the black hole shreds it and the whole thing explodes. Well, not the whole thing, just the star. Black hole doesn't care. This is an artist conception of this. I just learned this morning that Ruben can detect up to 20 of these every night, if we can tell what they are. So how do we do that? How do we find things that explode or that go or that change brightness in the sky? The way we do it is we take images of the sky before, we take new images, and then we difference the two. And in the difference, we look at anything that changed. So here's an example from the Deep Lens survey. Here's an old image, here's a new image, and here is the image difference with the supernova right here in the center. This speck of light is what you get when you difference, when you take this, and you literally this minus that. I'm vastly oversimplifying. There's lots of convolutions in between. So that's great, right? That's how we can find anything that changes. Well, not really. Even in this image, you can see that there are certain things that, maybe this is real or is this an artifact? There are these things that look masked out, and they're masked out because they would look awful because they look like artifacts. There are lots and lots of artifacts in this image differencing procedure. And this is a nice gallery of how things can go wrong from the Pan-STAR survey. I just love the nomenclature. If you want cool nomenclature, come to astronomy. UFOs, pianos, frisbees, arrowheads, and so on and so on. So one of the problems with this is that these types of things can overwhelm the real objects by factors sometimes up to 100 to 1. Our first surveys 10 years ago were that bad. And that's a problem. So what you want to do is you want to clean them up. The way people used to do cleanup was with graduate student power. You'd unleash hundreds of graduate students to literally look at these things because look at these by eye, right? You don't have to be an astronomer to tell that something funny is going on that's probably not real. But as I tell my students, anything that you can do by eye, it's very likely that now machine learning can solve for you. And so this developed a whole field of what we call real bogus classifiers. Classifiers that take the input data and basically answer the question, is this real or is this not real, aka bogus? So it started about 15 years ago with Bloom and Brink on IPTF. It got better through time. In 2015, this is on dark energy survey. We went from something starting at 100 to 1, we went to 1 to 3. So it's a suppression of a factor of 300. This is not just machine learning. It's by the way, these were all done with fairly simple random forests. Didn't even need convolutional neural nets for this. There's not just improvements in machine learning. There was also a lot of improvements in image differencing algorithms and so on. And now the state of the art is this tool called BRI, Bogus Real Adversarial AI. That's been deployed in ZTF. Dima Duev put this together some 5-6 years ago. And it's a fairly simple convolutional neural net that in the end does classification of whether an object is real or not. And here's how well it does. This is the ROC curve. And for those of you not used to looking at ROC curves, this curve, the holy grail is to make it look like the Greek letter, inverted Greek letter gamma. So it goes up and then this way, and this gets pretty damn close to it. It has about 2% misidentification rate and you pay about 2% incompleteness to get there. So that's fantastic. This would not have been possible without AI. So now we can clean up our sample and we can be left with just real objects. Real light curves. So how does the brightness of these objects change during time? These are a bunch of ZTF transients that I'm showing here. Now we want to know, what are these? So there are two types of games you want to play with this. One is you want to know what are you looking at in real time. These data points come, you may get one data point every 3 nights. And imagine having maybe 10 million candidates for interesting things. And imagine having maybe one telescope, so you can observe, follow up with the spectroscope, with a spectrograph or something, just maybe 1 or 2 or 3 of those candidates. So you have to down select from an order of 10 million to maybe 3. And each night you get additional data point, you start building up these light curves. And what you want is some classifier that as new data points are coming in, that classifier is giving you probabilities of, is this object interesting to my science program or not, and how that probability changed since yesterday. And at some point you set a threshold and go like, yes, I'm going to go and observe this. So there's been a lot of work on figuring that problem out. Here's one paper by Kyle Boone from 2021, applying generative models or putting together autoencoder-based generative models of transient light curves. So what's nice about this model, and where we've seen a lot of success, is combining putting the complex modeling of what the intrinsic transient looks like, what the light curve looks like, which could vary a lot from transient to transient, putting that into the neural network, and then the physics of what happens to that light due to its propagation through the universe, which we can write down as just plain old, not even differential equations. We can put that on the side. So we have these physics informed models that have both the neural network layer and the physics layer. And he manages to solve this problem basically to say, yes, this is a type 1 supernova, we should go and observe it, about a factor of 2 better in terms of contamination than the previous best problem from plastic. So this sort of thing is also taking over classification problems, and I think this is just going to continue. Another type of this classification problem is periodic variability. Let's say you don't care, let's say you've observed for a year, and now you want to see all these objects that periodically vary, and you want to understand what they are. Here's just a collage of of different types of stars with different types of variability. Those doing variable stars might actually know what they are. I think this one, the first one is, first one is Cepheid, I think. Here's a classifier. This is one of the early ones from Richards et al., but you can already see it's pretty good. These are different types of variable stars on the x-axis, like true classes on the x-axis and predicted classes on the y-axis. Ideally, you would get a diagonal here. You see that you pretty much get the diagonal in most cases. There are some cases where you don't get the diagonal. And the funny thing is, in those cases, you go to experts who usually look at this by eye and classify them, and the experts are going to disagree at the same level. So this is not the failure of the model. This is the failure of like those two classes maybe not actually being two classes, but maybe being one. So that has worked wonderfully as well. Moving on through this quick run through solar system. Here are asteroids in the solar system. When I say solar system, I always think asteroids, comets, dwarf planets, maybe big planets. We'd like to know where all these objects are in the solar system, because if we know where they are, we can figure out how planets moved early on in the solar system, and also we can figure out how many planets were there at the beginning. Right now, there's a very, very non-zero probability that we didn't start with the 8 big planets that we have right now, but we started with more. And something happened 4 billion years ago to eject one or more. So we want to, that's one of the big things we want to understand with Rubin. Rubin will detect between 5 and 30 times more asteroids than before. With such a larger sample, we should be able to reconstruct how the planets move through the solar system easily. There's also a practical reason to do this. Some of these objects come close to us and sometimes impact. This is a very bad day in Chelyabinsk, Russia in February of 2013, when just a small, like a bus-sized object entered the atmosphere and smashed about 1,500 windows. No, I think 3,000 windows, sent about 1,500 people to the hospital and so on. We'd like to find these before they hit us. And we can. We think we can find about 70% of really dangerous ones. We can answer where did the water come from. We can also find asteroids and comets coming from other solar systems, other planetary systems. So far, we know of 2. Both have been discovered in the last 6 years. With Rubin, we will discover anywhere between 1 per month to 1 per year. The reason for an order of magnitude uncertainty is we just don't know what's out there. So this will be super fun. And then, as I mentioned, we think that we may have started with more than 8 planets. There may have been a 9th planet. Well, it still may be there, but it just may have gotten ejected far out in the outskirts of the solar system. And if it's there, the theorists are predicting that it's roughly in the magnitude range that we should observe. So we have a better than 90% chance of finding it if it's there. So this is one of the most, I think, interesting or potentially impactful reasons that for LSST really to exist. But first, we have to identify all of these things in the data. And so there are 3 problems kind of in this identification, source, and discovery. Something we call asteroid linking, optimal detection of fast-moving asteroids, and then deep discovery for Planet 9. This is the linking problem. So how do we find asteroids? Let me ask people in the audience if they can point to the asteroid in this image. Anyone wants to try? The one on the right one? This one? This one?
Both.
Most people go for this one because it's in the middle, but because it's just, like human nature. It's this one up here. There's no way for you to tell. Anyone here speaks Greek? What does asteroid mean? It means star-like. They look exactly like stars. They're too far to be resolved. So the only thing that makes them different is their motion. So you have to take a few images and see them move, and then you know it's an asteroid. So now here, this was easy. You find an asteroid like this, and then you repeat this again, and then you kind of say this observation from today and this observation from yesterday were the same object. But this is what life looks like with LSST. In each image, we have up to 5,000 of these objects, and the combinatorics just becomes incredibly difficult. You can't really link them correctly together. So our problem statement for the computer scientists among us is given an order of 150 million 2D data points, find an order of 1 million groups of an order of 10 million objects that satisfy gravitational equations of motion. If you try to work this out, you discover that it's quite complicated. They're just computationally intensive. There are solutions. Here's an algorithm that one of our students, Joachim Moyens, put together for his thesis, where he does some clever transformation to take out the bending due to gravitation, and then turns all these orbits into lines, and then runs something like a Hopf transform. This works quite well. We ran it on existing catalogs, found 100 asteroids back in 2013, and then found 27,000, what was it, this April, with this new code. This is 27,000 of asteroids that were sitting in the archive for about 7 years because no one had the algorithm to dig them out. This is what makes it really fun. Also makes it really fun. We ran it on Google Cloud, so we got some coverage, yay. And Joachim got himself a nice award and a free trip to South Africa. But we missed too many dangerous objects. So these are our completeness plots. These are, I'm not going to go into details what these are. This is sine major axis. It's distance from the Earth. In essence, Earth is at 1. And yellow is good. We find almost everything that's far out. But these black pixels here, or purple pixels, are just half full. We find only 50% of objects that get close to the Earth, and that's because combinatorics of the problem becomes more difficult. So we're missing actually the objects that can hit us, which is unpleasant. So we would love to find an algorithm that can solve this without requiring thousands of GPUs, mainly because OpenAI bought them all, so we can't get them. And AI emulators may be a way to do this. So this is one of the areas of research where, if you want to jump into an interesting problem, please talk to me. We'd love to collaborate with someone who can help us develop these kinds of things. And I think crossovers with AGP are quite obvious, or possibilities, right? Because this is effectively track reconstruction, except that our tracks are a little bit more complicated. Yeah. All right, optimal streak detection. This is when that asteroid comes so close to us that it actually moves as you're taking the exposure. Think motion blur when you're taking a picture of a car on a highway, and then it's a line like this. And these are very interesting because if you see something like this, it means it's close. It also means it can impact. So 9 have been found so far, a couple of hours before impact, and then we would call up our friends and say, go out and take a picture exactly at this time, looking there. And that's how you get these beautiful pictures in here. We can predict meteors. Isn't that cool? So for optimal streak detections, our current algorithms lose about 50% of everything due to, well, them not being optimal for streaks. They're optimal for point sources. So one of the students who's actually here in Rijeka in Croatia, just like 2.5-hour drive from here, Karlo Mrakovic, has been working on this and put together a convolutional neural net for streak detection. This is the architecture to try to detect streak-like objects in images. So he takes an image, he splits it up into small pieces, feeds it to the network, and then asks the network, is there something that looks like a streak? And these are the sort of inputs that he gives. So here's the input, this is the truth, this is how we train, and then here's what the network outputs once it's trained. So this is how we know that it found something. Some details about how the model was trained. It actually wasn't that expensive. But I think this is the punchline. 2 times better than the systems that we had before. So here's a curve of green is what LSSD finds right now versus the length of the trail. Note how it starts falling off. And then here are the objects that we're finding with the CNN. It's here when the trails get long. This is it gets about factor of 2 better than LSSD. And these results are about 3 days old, so they're going to get better. So again, AI could help save the world. Although this one sort of started by destroying it, so I don't know, maybe not a good analogy. The third thing I want to show you is deep exploration of outer solar systems. So I mentioned that there might be an Earth or Neptune-sized planet out there, and we want to find it. It might be bright enough so that Rubin just goes ahead and see it, and that our other algorithms find it. But if it's not, we want to go and try to find objects that are fainter than what we could see on a single image. So how do you do that? So here's an example. These are 3 images of an asteroid that's moving. That's the thing in a circle. And how would we increase the signal to noise of this asteroid from these 3 images? Well, we could take the first one, and we can take the second one and overlay it so that the asteroid falls on top of the asteroid in the first image. We can take the third one, do the same thing, overlay it, then add all these together and increase the signal to noise. Right? This here is the PowerPoint algorithm for shifting and stacking. This is when you do it right. So you go from something that's quite faint to something where SNR is now high, and you have confidence in what you've seen. The challenge here is that to do this, you need to know that the asteroid is already there. So you need to know how to shift these images to make this work. But we would like to find asteroids that are not there. Sorry, we find asteroids that are there, but that we don't know are there. So how do we do this? What if you don't know where the object is and it's undetectable in individual exposures? Well, we try all possible motion vectors. So instead of building this one coad, we build billions. We try out every hypothesis. Could it be moving this way? Let's shift all the images. Let's stack them. Let's see if anything pops up that looks like this. As you can imagine, that's not cheap. That's quite expensive. This technique is called shift and stack. It's also called digital tracking in other contexts. It works. Here's an example of a Kuiper belt object, a very distant object found from, what's this, 1, 2, 3, 4, 5, 20 images. On each individual image, you practically see nothing. You might convince yourself to see something here, but when you shift them and stack them, you get that. And we use GPUs to work through billions of trajectories this way. But if we want to scale this up to Rubin, and we've done this calculation, we need an order of 5,000 GPUs working 24/7 over 10 years. And again, OpenAI bought them all. So we would love to come up with an algorithm, and this is also likely to be an excellent AI problem that will emulate this computation, but do it more efficiently and more cheaply. And I have kind of hand-wavy reasons why I think that's possible, because in these computations, there's lots of math that gets repeated unnecessarily between different orbits, and I think that's what the AI can learn, how to not repeat that math. So again, in the spirit of Smash, if you want to think about these things and collaborate, this would be one thing to get involved in. All right, if this is solved, by the way, the impact is huge. You get a Nobel Prize for Planet X discovery, and I think physics now is the default category for anything. And we also learned we get a Turing Prize as well, because this is all computing. But you also find hundreds of dwarf planets. You remember when Pluto was a planet? Who here was born when Pluto was still a planet? Who's old? So there could be hundreds that are bigger than Pluto that are still out there. You increase the number of known solar system objects, et cetera, and you can also help with planetary defense cases and to find dangerous asteroids. All right. So final note, I know I'm running out of time, over time, but I think this is an interesting one. And it's qualitatively different than the others. LLMs. So let me tell you about a place called Višnjan. Višnjan is a place in Croatia. There's an observatory over there. It's an hour and 20 minutes drive from here. If you don't know what you're going to do over the weekend, you might want to visit it. It's one of the most beautiful observatories I've ever seen. It's built as a Romantic church. They have a 1-meter telescope. What they're famous for, though, they discover asteroids, but what they're famous for is their educational program. They bring in kids at elementary school level, high school level, college. Virtually most present-day astronomers from the region have gone through that program at some point. I am one of those people. And they have those kids work over the summer on interesting problems, on interesting projects. So this summer I went to teach over there. It's called the Višnjan School of Astronomy. Highly recommended. I went to teach this summer, and the way you teach there is you get like these 20 interested bright kids, and then you have to pitch them a project. What are we going to do? So this was my pitch. I said, we're going to build the fastest, meanest online asteroid position lookup service ever. So this is a fairly simple problem in the sense that you want to know which asteroids are at a particular time at this particular place, which asteroids are there. It's a completely doable project. Newton has solved it, but all the services out there that exist take like 10 to 60 seconds to do it. And for LSST, we needed to make this faster, so we wrote some code to make it faster, and now we can do it in 10 milliseconds. It's always fun to go like 3 orders of magnitude. And I said, we're going to take that code and we're going to make it into an online service. Our group is going to make it into an online service, and we're going to do it in like 6 days. Will this be better than like, Bible chapter 1? 6, not 7 days. Actually, yeah, he rested on the 7th day. So this was the plan. And so I got a team of 5 very excited high school students. High school students never change. Like, look at the guys trying to impress the girls. So this was our working environment. It's really like the proverbial garage with a startup with a whole bunch of computers. And the thing that I do with these projects is I tend to forget that high school kids don't know everything they need to know to build this. I tend to be over optimistic. So when we sat down and we went around the table, like, all right, so who knows Python? Well, I know how to write a for loop. Anyone use Linux? Not quite. So we quickly discovered that none of us actually knew everything that we needed to build this code. So we recruited a 6th team member for measly $20 per month. We recruited ChatGPT 4.0. And then the first 2 days, I taught the kids how to buy their own server on DigitalOcean and how to go install a virtual private server and how to set up this software as a service. And then they started to talk to ChatGPT to build the rest of the code. So here's some of the conversation. This is how we started. We told it, look at the API described at here. Can you write me some JavaScript code that will access that API, take the result, list the JSON objects, and format it into an HTML table? And it wrote the code, and it worked. Just copied and pasted this, and it just worked. So, and not just that, I don't have that in a screenshot, but it actually explained how it works. It did it better than I could. Thank God for tenure. I might get fired tomorrow. So then we continued talking to it. Excellent. The API in question takes the argument T, a float, RA, a float, and dec, a float. Astronomers recognize this as time, right ascension declination, so 2 coordinates, and radius, the size of the field of view of the telescope. Can you add this to a form which asks blah, blah, blah? Goes ahead, adds this, makes you a form. And we kept talking to it. And then we got to a problem where it started giving us, could not establish, we're getting this error. Do you know what that is? Oh yeah, sure, you have to adjust your course policies. So you go ahead and do that, and it tells you actually how to do that. And so we continued talking to it like that for about 2 or 3 days. And then in the end, we kind of got bored and said, well, we didn't get bored. We were like, hey, what else can we do? Well, we'd like to know how long it takes. So can you add that to the display? And it happily did that. So after about 3 or 4 days, we had a website. This is all ChatGPT built by talking to it. There were some pieces that we did by hand because the kids started looking at the JavaScript, which they've never done before, and then realized how it works, talking to ChatGPT about how it works, and then started doing it manually because now it was fun. This was their design. The aesthetic is interesting, right? Because this like reminds me of internet in 1995. But this was all them, like our 2024 high school kids have built something that, or like intentionally, they put the backgrounds and everything. I think if blink tags still worked, they would make something blurry. So this was it. They made it work. You can actually go to this website. The only thing we didn't get to is we didn't get to put it into cron tab so it gets refreshed for every day. So you have to type in the date when we deliver the project for this to actually work. So type in August 15th, and then it'll work. And it still works. And we did it ahead of schedule. We got that done by Saturday, rather than, I think we planned it for Sunday or Monday. So ChatGPT here was an incredible accelerant, and none of us actually knew JavaScript when we started this, and we learned some JavaScript in the process. So why did I spend like an extra 10 minutes talking about this? Because I think we talk a lot about where we can use this for just like solving specific science problems, but the more generic problem of how do I interact with my data, and like especially how a non-specialist explores data sets, I think that's going to also be quite a sizable game changer. I think there's just the tip of the iceberg that we see here relative to what's possible. You know, we deliver these huge data sets in SQL databases, and then we expect our entire community to learn SQL and to learn how to operate these databases. And they usually manage to learn like the very basics and to kind of muddle through. But now they can start talking to an AI who's going to start constructing queries for them, who's going to know the structure of the database, who might be able to put together the proper join, and the join that's not going to take forever to execute on the actual database system. You might be able to put together complex visualizations, enable data exploration, where you ask an AI, hey, based on what I've seen, what you've done for me, can you change it and do it differently? And then it comes back in 5 minutes, not 5 minutes, 5 seconds, and does that for you. Could you give it complete research tasks? I haven't tried this. It's on my to-do list after this conference, but I want to take a paper. I want to take a data set that I know can resolve something from the paper, and I want to see if I can upload some version of that paper to O1 Preview and ask it, can you find proof for what's predicted in this paper in this data set? It's probably not going to be as easy as that, but like that's where we're heading. We're heading towards having a team of AI-powered research software engineers and analysts to kind of effectively sit next to you and help you get through this. And not just me as a professor, but like each one of us, one of our graduate students, if we teach them how to use this properly, can effectively have a really good 24/7 tutor and a software engineer next to them to help them work through this. And it's not just us. I put in here a screenshot and a transcript from a podcast called All In. It's a bunch of Silicon Valley venture capitalists talking about like what's going on. It's actually really good. Where they describe exactly this phenomenon that's going on in industry right now. People are realizing that what you used to hire an analyst for, now ChatGPT can do for you, and actually much faster and much cheaper. So this is going to be happening throughout, and we need to figure out how to leverage this, how to turn this into something that our students can use and be more effective in exploring these large data sets. So I went way over time. I apologize for that. I hope this was interesting. This is my last slide. My message is that Rubin is finally here. This is a big data set. It should be as impactful as the Webb Space Telescope or Hubble Space Telescope. It's starting next year. The next challenge is how to extract all this knowledge from the data. And I think AI will play a major role in doing so. And the applications of AI are still novel in astronomy. So if you're a computer scientist or a physicist, or you're just interested in solving interesting problems, this is a really, really fruitful place for collaboration. So I'll stop here and open it up for questions. Thanks.
Great, thanks, Mario. Wonderful talk. Questions?
Yes, thank you for a really excellent talk. My question is about, you talked about asteroids. What changes if we talk about comets? Because I remember this movie, Don't Look Up, there was a comet sneaking up on us.
So two things change. One is comets get an additional, you can think of them as having a little rocket engine of their own. As they expel material, they get what we call non-gravitational forces. So when we compute their orbits, we have to take into account some of those non-gravs. That's the easy part. The hard part is that comets are fluffy. So they don't look like point sources. And remember when I talked about real bogus? Real bogus is a filter that's very simple to mistrain, because you can teach it that a real object is something that looks like a star, and a bogus object is everything else, in which case we lose all our comets. So I think we're going to, when we're training real bogus, and it's happening right now, we have to be very careful to actually invert the problem. the real bogus classifier shouldn't look for real objects. It should look for bogus objects. It should look for artifacts. It should try to identify known artifacts. It should be trained as an artifact finder. And then everything else that it cannot conclusively say is an artifact, it should let through. Because that's a better failure mode. Because then, you know, the scientists can go ahead and say, oh, look, that's a comet, or, oh, look, that's an artifact that we didn't have in the database of artifacts, and we're going to update the training. So that's my biggest fear for comments, that we somehow lose them with real bogus. Ask me again in a year.
Questions? Yes.
Hi, thanks for the presentation. That was really nice and fun. For the shift stacking one, so you were suggesting using AI just to avoid like checking all of the yes. But would you need an AI that limits the trajectory to only the physical one? Because I can imagine if you have a bunch of like, you know, noisy images, you can always find a stacking that will create some kind of, you know, bright one, but it's just like by doing this weird, like in physical.
Yeah.
Yeah.
No, you absolutely. You want to train it to allow only for physical shifts, or for physically meaningful shifts. So you might start with just allowing linear translations. It actually, for Rubin, we need to go one step beyond, because we want to stack over like 2 weeks or so. And there you get the bend in the orbit. So remember when I showed that hybrid model where we had AI and then the physics part of the model for supernova detection, the Parsnip Kyle Boone's model. We'd need something like that, where we separate out the physics that we can explain, and then pack the rest into AI. So that's why it's a fun problem.
Thank you for the nice talk, but I was a bit disappointed because because you had 4 physical, so the 4 science cases that LSST was gonna do, and for my PhD I was really reading your paper on the tomography of the Milky Way with SDSS. So I was expecting to at least touch the Milky Way mapping, but you didn't say anything, perhaps?
I actually cut out a bunch of slides after I saw your talk this morning, because I was like, oh, this is covered. Great.
Do you want to tell us something?
It's I think you can tell us more than I can. It's you know, it's a problem of how do we find clumps? How do we find anomalies? How do we find things that match models like you showed? There are people working on it. There's like folks that are closest to me. Nora Ship just started at UW as a faculty member. She's going to be looking at finding streams in the galactic halo. Anna Bonazza, who's originally from close to Vishnan, actually, is now at Carnegie Observatories. You know, she's been looking at these kinds of objects in the Gaia, and we'll be looking at them in LSST. I think that community has had so much to do with Gaia that they haven't really started thinking hard about Rubin, which I think is the rational choice. But that's going to change in about a year. When our data starts coming out, then I think you're going to see all these the techniques that folks have developed for Gaia applied to Rubin. So I kind of I saw it covered and intentionally skipped a bit that piece. Yeah.
Good.
Not because they don't like it. I'm actually getting back to that after we find Planet 9 and get our Turing Award.
Okay, more questions? Okay.
It's not a question, but I mean, it is a question, but not necessarily to your talk, especially, at least not the science part of it. But well, at the end of every ML and / physics conference that I've been to, I always ask this, I end with this question. I mean, universities usually pay for Mathematica. They pay for, you know, license, you know, paid versions for everything. But how long do I have to wait until we pay for ChatGPT? I mean, really, we can do away with. No, I shouldn't say that. We can augment the strength of a PhD student. with the ChatGPT.
Estonia. University of Tartu will provide you with ChatGPT.
So bring your ERC grant over there. It's a good question, and I know that there are sometimes bureaucratic obstacles. Like I have that problem as well. I actually, per National Science Foundation rules, I cannot charge my $20 a month of ChatGPT to my grant because I cannot prove that I have only used it to work on the problem of that grant. Right. So I have to, right, like if you have something that you can use for something else, they don't allow you to put it on your grant, which to me is just like my head explodes. So we find other ways to pay for it. It's relatively low. The thing that I think we should figure out is how do we get this in the hands of all of our undergraduates, especially for teaching, right? Like we have these large introductory classes to astronomy that have, like every quarter we get about 100 to 200 students. And you can imagine, no matter how many teaching assistants you have, those students do not get like 5 hours with a teaching assistant per week. These things are really good teaching assistants. If you give them the right prompt, they can actually walk you through a problem. They can explain how to solve it and so on. So I think in combination with professor and TAs explaining the material or introducing the material and giving some problems and then having students work effectively with their own tutors, we could make significant difference in how much we teach. The only proven educational, what's it called? Intervention, that's the phrase. The only educational intervention that is proven to work at like few sigma standard deviation is one-on-one tutoring. Everything else that we've come up with, since Greek times onwards is like, a sigma here, a sigma there, not quite clear if there's a signal. One-on-one tutoring, the amount the students learn goes sky high. And the reason why we do that is it doesn't scale. But now it could scale. So like one of the things I want to do next year is I'm trying to develop this course where we'll do just that. So ChatGPT is good enough to teach you basic astronomy because that like at a 100 level in the US, so first year undergraduate. And I think that's where huge opportunities lie. Just universities have to embrace them. And right now there's a little bit of this movement of, oh my God, am I going to lose my job because of ChatGPT? So therefore we should keep them out of the universities. And we somehow have to help people get over that and see it as a tool, as help rather than as a threat. It's like back in the Industrial Revolution, there were strikes by textile workers for going against automation and the big, it's probably not called that way, like knitting machines or whatever they're called. And they would go in and break them and so on. The phrase Luddite comes from those strikes, right? And today you wouldn't do it manually. There's no way, right? Like we wouldn't be able to get all the clothes for everyone on Earth if we did it manually. So we're going through that kind of, I think, in education, and we have to figure out how to make these enhancements more palatable. Sorry, longer answer, but that's I think that's the place where we really need to work in universities.
Food for thought.
So a follow-up question. In my experience, ChatGPT and similar tools, they are like very attentive, very like trying, but not very smart student. So they can give you answers that are formally correct, but somewhat incomplete. You start asking for clarification, and you can easily lead them to some complete bullshit. Okay, so if I have some domain knowledge, I can catch this moment, and I know that I have to check what is going on. But is it safe at this stage to give these tools to students? Apparently, I'm at the age when I'm becoming a little bit horrible. So I'm not that old. But we have to, first of all, teach the students not to trust this and to follow up the answers they are getting from these tools. And can we really teach people that? I mean, people are lazy.
I think this is So two parts of the answer. One, I think we need to figure out how to do this. And this is where the research comes in. We have to try this and learn where the mistakes are. But the second answer is you have to compare the potential negatives there against the baseline. And the baseline right now is that the student doesn't learn at all. Like in these large classes, if they don't have access to the TA and they don't have time or whatnot, and it's just they feel it's boring, they'll just copy and paste it somewhere from online where they found it, right? So I don't know what the answer to your question is, but I think my sense, just based on me pretending to be a student and asking ChatGPT thing, is like oh, this is powerful. This is better than just Googling. Yeah.
I think that's what you just said, like, that the alternative is they just Google it, look it up on the internet, and then they copy it over. And then in your ChatGPT, at least you can ask, right? Well, yeah, but right? And it's like a pretty free, like, because right now, yeah, they don't learn from like talking to a professor who's at the people like the event, right?
Yeah.
They're talking like they're the internet, but talking stuff.
And the one thing you said is you're right. ChatGPT is actually trying to be too nice, right? So it will accept anything you tell it. If you tell it green is blue, it will go, oh, I apologize. Yes, green really is blue. So like that's one of the how do we make it a bit more resilient to malicious user input? Let's put it down. Because I know what I was like as a student. Like first thing I'm going to try is to break whatever the professor gives me, just to prove a point. Yeah. Thank you.